So basically, if you see here in the quick sort, generally the C recursive function we write here as, so we write generally here as void quick sort, and basically here we are passing one integer array, we are passing here the first number, and we are passing here the last number. And then I'll write first of all, as we all know that how the quick sort work. So I'll write here the code, and then we say that if my first is less than last, then we are going for partitioning, that is j is equal to, we're calling for a partitioning function, partition of a comma first element comma last element. So we are not taking the next one, it is last element we are calling. Then we are calling for quick sort, passing a from first to j minus 1, and again we are calling for quick sort, passing array a j plus 1 to last, right? So this is in general a recursive function. Then in partition function, I'll write here partition function. So because partitioning function is returning j value, so it will be a int partition. In that function, here I'll declare int integer array a. Again I'll use here concept of int first element and int last element for that particular array. Inside this, I'll declare here ij and temp for swapping. Okay. So last time, if you remember, I told you about the do while loop. So basically, do while loop, if I start my I from the first, then I'll do first of all do I plus plus and then put into the while loop. Without using a do while also, you can simply use here a while loop. So let's say I use here a while loop. So my j is starting from L, whereas basically my I will start from the first. So I'll use here while loop. So because I am declaring my first element as a pivot element, so obviously my I will basically start from first plus 1, because my first is a pivot element. And then we will put first of all outer while loop while I is not intersecting j. So till the time, what I supposed to do here, I supposed to perform the operations. Okay. So here again we will do here one thing, while my a of I is greater than, we need to have pivot element here, so I'll say pivot is p. Okay, and here we can say this p is equal to a of first, because here we are taking our first element as a pivot element. So I'll declare here p is equal to a of first. Okay, so while a of I is greater than the pivot element, and I is basically for a smaller value, so here we'll write a of I is smaller than the pivot element. It's a mistake from my side, because we want I to be a smaller than pivot a of I. So here we say while a of I is smaller than pivot and basically our I is basically less than or equal to the last element. So here till the time what we are doing here, we are basically going further. Okay. So here a of I is less than pivot and our I is less than or equal to our last element. What we are doing, we are incrementing I plus this. Right. Now this while loop will terminate when basically my a of I is greater than pivot. Now we'll go for j. So while a of j is greater than pivot, what we supposed to do here? Supposed to simply write j plus this. So j minus minus, because j will come towards the index 0. So here we write j minus minus. Now next thing is, now I and j will stop once a of I is greater than pivot and a of j is smaller than pivot. So what we supposed to do? Supposed to check the value of I and j. So here we will be checking value of I and j, and if we find I is not intersecting j, so that means if our I is less than j, what are we supposed to do? We are supposed to swap a of I with a of j. So here we will swap a of I with a of j. So what we will do here, temp is equal to a of I. Then we will say here a of I is equal to a of j and a of j is equal to 10. Right? So this first condition, that I is less than j, but this I and j stop here and my I is actually greater than j. I is intersecting j. So automatically what we supposed to do, this while loop will also terminate here and we supposed to swap pivot with j and we supposed to return the j. So here this while loop will terminate, and then what we supposed to do here, we simply write here at the a of first position is equal to a of j, and at a of jth position we supposed to put our pivot element and we supposed to return j. Okay, here completes the function. Okay, so there are basically 4 steps involved in that. First step is we are doing I plus plus till my pivot is greater than a of I. Next time we are doing, once this stops, next time we are decrementing j till our pivot is greater than pivot smaller than a of j. Then I and j will stop, then we'll compare here I and j. So if my I is not intersecting j or it is not greater than j, we'll simply swap a of I with a of j and will continue in while loop. If this if loop will not execute, that means let's say if my I is greater than j, will not go here, if loop will not get executed, and we will simply swap a of pivot with the a of j and will return j to this particular partition function. Okay. So basically, this is in general the quicksort algorithm. Now let us go for the time complexity of quicksort. If you look at here, this partition, basically in partition I and j are actually intersecting each other at every level. So this approximately traversing the complete array for n times, right? This quicksort, basically here, this is a summative function. It is a recursive type of function. So here this will execute array which will go from 0 to j minus 1, that is 0 to j. So this will approximately work for 0 to j. Whereas this particular quicksort function, it will go from j plus 1, or you can say approximately, I'll take here j to L means our n minus 1 index. So this will go for j to n minus 1. Okay. So based on that, we are actually going to write a recursive relation over here for time complexity. Okay. This is recursive function, and the relation that we use to count frequency and time complexity is called as the recurrence relation. This is called as the recurrence relation. So we'll try to establish a recurrence relation, and then we'll see what is the best case, worst case, and average case for quicksort. Okay. Now look at the analysis of quicksort. So basically, the quicksort, if we see the time complexity of quicksort, you can say the speed of execution. Actually, it get determined through the three things. Okay, the first thing is here, that is the recurrence relation. So here we have to establish first of all the recurrence relation. So it is a recursive type. So basically here we say running time of quicksort. So here we say running time of quicksort will be given by running time of left partitioning. Running time of left partitioning plus run time of right partitioning plus we say time required or time spent in the partitioning the elements at partitioning function. Time spent in partition. Right. So basically here we can easily understand the time spent in left partitioning. So that will go from 0 to j minus 1. So I can say here, let's say t requires the time spent in left partitioning. So approximately there are j elements. So right here t of j plus time spent in right partitioning. Okay. So there are j elements in the left partitioning. Right partitioning, actually there are index will go till n minus 1. Right. So in the right partitioning, time required will be right here as t of n minus 1 minus j. So that will be plus time of t of n minus j minus 1, that will be in right partitioning, plus time spent for partitioning. So basically, in partition function it is parallelly working on n number of elements, and say some c times we are calling for partitioning, so write here c into n. Okay, so this is called as basically the total time required for the quicksort. Okay, so this is a function, total time required for the quicksort. Now we'll see what is the best case condition, what is the average case condition, and what is the worst case condition for quicksort. So we'll see the best case condition first of all. What condition is called as the best case condition. So in case of best case condition, see every time, say this is my array. So every time the pivot element I am selecting, its position always get at the middle. Okay, next time even though I select this particular pivot element, its position is in the middle of element. So that means every time I am dividing that particular array into two equal halves. Okay, that is actually ideally a best case condition. The pivot element position I am getting always at the approximately middle of the array. So that time what will happen, every time this array is getting divided into two equal parts, right? One part is of n by 2 and the right part is of n by 2. So here for best case condition, we are writing the equation as t of n is equal to, j will be now n by 2, so t of n by 2 plus n minus j minus will be of n by 2, so that is t of n by 2 plus c into n. So we'll write here in best case condition, the equation is t of n is equal to 2t of n by 2 plus c into n. So this is actually a best case equation, that is left and right partitioning is same because my pivot element always find its middle position. Okay, so selected pivot element always get at the middle. I will keep on solving this. So in this equation, let's see if I put n is equal to n by 2. So this particular equation, this will look like, if I put n is equal to n by 2, so this equation will simply look like t of n by 2, this will be equal to 2 into t of, now instead of n I am putting here n by 2. So t of n by 2 into that particular 2 plus c into n by 2. Okay. Now if I put this whole equation over here at this place, t of n by 2, if I put this whole value, I'll get here now t of n is equal to 2 into 2 t of n by 2 plus c into n divided by 2 plus c into n. Okay, and if I simplify it, I'll get here as 2 square, because 2 into 2, 2 square into t of this n by 2 into 2 here, t of n divided by 2 square plus this 2 and this 2 will get cancelled, and I'll get here c of n plus c of n, which is equal to 2 square into t of n divided by 2 square plus 2c of n. This is for second pass. Now for third, if I go for third relation, it will give 2 cube into t of n divided by 2 cube plus 3 into cn. Right? Now if you look at the termination condition for recursive call, what is the termination condition? My I is less than, my first is less than last, till that will execute. If my first is equal to last, that means there is only one element remaining. So that means here t of 1 is basically my termination condition for recursive, that particular function. So here that means if my n divided by 2 raised to some value of h will be equal to 1, that time my loop will get terminated. So here if I write like this, 2 raised to h into t of n divided by 2 raised to h plus h into c into n. For that particular some point, my the condition will actually work and the loop will, recursive function will terminate. So for some value of h, if I simplify it further, I'll get here n is equal to 2 raised to h. Now this h is basically at the exponent level. I want to bring it at the base level. So what I'll do, I'll take log on the base, both the sides with base 2. So taking log on the both side. So here if I take log on the both side, I'll get here log to the base 2 of n is equal to log to the base 2 of 2 raised to h, which is equal to h. So I'm getting here h is equal to log to the base 2 of n, and I'll put this value in this particular equation. So if I put this value here, what I'll be getting here, 2 raised to log to the base 2 of n into t of 1, because we assume n divided by 2 raised to h is equal to 1, plus h is log to the base 2 of n into c into n. So here this will be 2 raised to log to the base 2 of n, this value is n according to logarithmic formula, t of 1 is very insignificant, plus this will be c into n into log to the base 2 of n. I have just done the rearrangement of this particular term over here. Okay. Now according to this particular our time complexity expression here, the driven factor is n into log to the base 2 of n and not only n into t of 1, because n into log to the base 2 of n has a much higher significant and driving power than n. So we generally write it as approximately the complexity, we write it as a best case, generally we denote using omega of n of log to the base 2 of n. This is worst case time complexity. But in general, people write O of n to the log to the n. Okay, but this is actually correct. But in general, you find that it is given as O of n to the base log 2 of n. This is a best case time complexity of the quicksort. Okay. The recursion relation that we will see now, the recursion relation that we have written for quicksort is T of n is equal to T of j plus T of n minus j minus 1 plus C into n. This is our recurrence relation, right? Now, the worst case condition for quicksort, the worst case condition is that, so this is basically my array and this is my pivot element. And next time generally we have seen best condition, the pivot position comes at over here and we get basically the equal partitioning. Next time again this is my pivot element and the pivot element position comes at the middle, something like that. That we have seen. We need a minimum number of comparisons or minimum number of recursive calls in case of best case. But in case of worst case, now what happens here? In the worst case, my pivot element position is always be at the first or always be at the, or you can say last. Like let's say I have selected this pivot element. So here after sorting the array, my pivot position comes over here. Again this array will remain. Let's say I have selected this as pivot element. So this element's position comes again here as the last element and this array is remaining over. Right? So every time basically what is happening, I am getting the pivot element position either at the last or at the first. Right? So that time here the condition will be there will be not equal distribution of the array. There will be always a unequal distribution of the array and the pivot element always come at the last. So here it means if I want to define the worst case condition recurrence relation, so here that means let's say here I assume my j is equal to always 0. I am getting my pivot element as by default first element, right? So if j is equal to 0, my time complexity T of n, I'll write it as T of 0 plus T of n minus 1 minus 0 plus C into n. So that will be equal to T of n is equal to T of 0 is negligible. So only I'll take T of n minus 1 plus C into n, because my pivot element always be at the last or at the first time. So there will be only n minus 1 arrays remaining for the next recursive call. Okay. Then I'll try to find value of T of n minus 1. So here in similar way, if I put in this equation n is equal to n minus 1, I'll be getting here as T of n minus 1 is equal to T of n minus 1 minus 1 plus C into n minus 1. So I'll get here as T of n minus 2 plus C of n minus 1. Okay. So here if I put this value of T of n minus 1 in this equation, I'll be getting here as T of n is equal to T of n minus 2 plus C of n minus 1 plus C of n. Okay. So like that way, I'll get further as if I find T of n minus 2 value, I'll be getting it value as T of n minus 3 plus C into n minus 2 plus C into n minus 1 plus C into n. Okay. So like that way, if I go further, at some point of time, the termination condition will occur, and termination condition is at T of 1. So that T of 1 will be equal to, T of 1 plus, here that will be C into 2, because 1 plus 1 is 2, C into 2 plus C into 3 plus, so like that way n minus 1, n minus 2, n minus 3, n minus 4, like that way it will go till, what you can say, 1 minus 1 is 0, like that way it will go till T of 2, 3, 1, 2, 3, like that way. So it will start 1, 2, 3, 4, 5 like that, n minus 3, n minus 2, n minus 1, n, like that way it will go. So C into 2, C into 3 plus dot 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 plus C into n minus 2 plus C into n minus 1 plus C into n. Okay. So that will be equal to T of 1 plus, I'll remove C outside, and this is basically the summation of I is going from 2 to n of I. Because if I take C outside, that will be 2 plus 3 plus 4 plus 5 plus dot 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 n. Summation of 2 to n element. Okay. So which will be written here as, we write here I into I plus 1 divided by 2. So in terms of n, the answer will be T of 1 plus n square, C into n square, and approximately n square is driving factor. So here we write the time complexity as O of n square. Okay, this is a worst case. We can understand best case condition is, what is best case condition here? The best case condition is that pivot element position is always getting at the middle. Pivot position I am getting at the middle. I am not talking about selecting the pivot position. I am talking about the pivot element which I have selected to partition the array. After partitioning, its position always come at the middle. This is the best case. Worst case is what? My pivot position is always at the end or at the first. It is always at the end or always at the first position after partitioning the array. Okay. Now we will see the average case condition for the quicksort. Now we will see the average case analysis. So we have seen basically, best case, the pivot element position is always after partitioning comes at the middle. In worst case, the pivot element position always comes either at the first or at the last index. In average case, the middle condition is considered, that it can come at any point between the middle to the first or last. So we go for now average case analysis. So in average case, basically we know the partition relation which I mentioned here, T of n is equal to T of j plus T of n minus j minus 1, right? So here in case of average, the j variable will always go from 0 to n minus 1 for this j. It can take any value from 0 to n minus 1. So if j is taking 0 to n minus 1, then this function T of n minus j minus 1, so that will go from, when j is equal to 0, T of n minus j minus 1, that particular function, it will become now n minus 1. And when j is equal to n minus 1, so that function will be going from n minus 1 to 0. So ideally, when this j goes from 0 to n minus 1, this T of n minus j minus 1, that will go from n minus 1 to 0. Okay, so I think this point is clear. Now with this basic, the recurrence relation, that we can simply write here as T of n will be equal to this T of j, it is going for j is equal to 0 to n minus 1. So here I write summation of j is equal to 0 to n minus 1, because our T of j is going for this, plus we write here generally 1 by n into, this is a standard formula, plus again for this j is equal to going from 0 to n minus 1. Actually j is going from n minus 1 to 0 for T of n minus j minus 1. I just put it similar, j is equal to 0 to n minus 1 of T of n minus j minus 1, and plus this C of n here, C of n. Now as this j, it varies from 0 to n minus 1 for T of j, and this j is varies from n minus 1 to 0 for n minus j minus 1, right? So from this equation we can simply write here as a standard formula, summation of j is equal to 0 to n minus 1 t of n minus j minus 1 will be equal to summation of j is equal to 0 to n minus 1 t of j. This comes same. Okay. Here, if you put those values and find out the answer for both of this, the answer is same because here j varies from 0 to n minus 1 for both the equations. Okay. इसमें रहेगा उल्टा आएगा इसका आंसर, इसके रिवर्स आएगा, but the thing is that answer will remain same for both of this summation. Okay. So here from this we can write, since both these are equal, this part and this part, simply we can write here that if you put this in above equation, I'll get here as the value for t of n will be equal to, now we are taking here also t of j, so that will be 2, we are adding this, so 2 divided by n into summation of j is equal to 0 to n minus 1 plus c into n. This is a standard recurrence relation that we establish here. Okay. Now here, if I want to solve further, this will take another 30 minutes because the integration is involved to simplify this particular average case, and then I have to apply here a limit continuity formula and then get the answer. But it's not required in that detail. I'll simply write here the average case answer. If we solve further, we get here the average case complexity for this quicksort here by solving this recurrence relation as O of n log n. Okay, I don't want to further solve that because it will take huge time and this is not expected at this point of learning. Okay, what you have to remember, first thing is about what is the best case for quicksort. The best case for quicksort is my pivot position is always at the middle. What is the worst case for quicksort? The worst case for quicksort is that my pivot position after doing a partitioning is always at the last index or at the first index. And third thing is average case between these two. It generally divide the array between 0 to n minus 1. Okay. So for best case and average case, the time complexity is O of n log n, and the worst case, the time complexity is n square. So already seen worst case and best case. Average case, actually this is a recurrence relation, but it is not expected to go further, it's too complicated. Okay, so here we finishes with the quicksort, and we'll see now we'll start with the heap sort.